Hello students, Professor Piggy here. Today we are trotting confidently into the barnyard of server application attacks, where web servers accept input from users all day long, and the wolf lurks nearby hoping to slip in something nasty. Web servers are highly susceptible to attack because they commonly accept data from users, and anytime a system accepts input, it must assume that input could be malicious. For the Security Plus exam, you must understand how improper memory handling and injection flaws allow attackers to exploit server applications. Let us begin with memory vulnerabilities, which are weaknesses related to how an application allocates, uses, and releases system memory. Developers are responsible for implementing secure memory management techniques in their code because poor memory management can lead to instability or exploitation. When memory is not handled correctly, applications may suffer from memory leaks, buffer overflows, or integer overflows. These issues are not merely performance problems, they can become security vulnerabilities that the wolf attempts to exploit. A memory leak is a software bug that occurs when an application allocates memory for temporary use, but fails to release that memory after it is finished using it. Over time, the application consumes increasing amounts of memory, which can degrade system performance. In severe cases, the application may exhaust available memory and cause the operating system to crash. An early indicator of a memory leak is a system that becomes progressively slower until it is rebooted, and administrators can often observe excessive memory usage in tools such as Task Manager. Now we turn to buffer overflows, a favorite trick in the wolf's dusty playbook. A buffer overflow occurs when an application receives more data than it is designed to handle, or receives unexpected data that exceeds the allocated memory buffer. A buffer is a defined area of memory set aside to store data temporarily, and applications are only supposed to access their assigned buffers. When too much data is written into the buffer, it can overwrite adjacent memory locations, potentially exposing sensitive memory or altering program execution. A buffer overflow by itself exposes a vulnerability, but a buffer overflow attack occurs when an attacker deliberately exploits that vulnerability to inject malicious code. This technique often includes a sequence of no-operation instructions, commonly represented by hexadecimal 0x90, followed by the attacker's payload. The goal is to overwrite memory in such a way that the system executes the malicious code. This is sometimes referred to as memory injection, and when successful, it allows arbitrary code execution under the context of the vulnerable application. Preventing buffer overflow attacks requires strict input validation, proper bounds checking, and secure coding practices. Error handling routines and validation mechanisms reduce the likelihood that unexpected input will be processed. However, they do not eliminate all risk, which is why vendors release patches and hotfixes when vulnerabilities are discovered. From an administrator's perspective, the mitigation is straightforward and exam critical. Keep systems updated with current patches so that known buffer overflow vulnerabilities are remediated. Next, we examine integer overflows, which occur when an application attempts to store a numeric value that exceeds the maximum size supported by the allocated memory space. For example, if an application uses 8 bits to store an integer, the maximum value it can represent is 255. If a calculation produces a result larger than that limit, the value wraps around or produces an incorrect result. This can cause logic errors, security bypasses, or unexpected behavior within the application. Integer overflows can be prevented by validating input values and ensuring that variables are sized appropriately for the expected range of data. Developers should implement proper error and exception handling to detect and manage unexpected numeric conditions. On the exam, remember that both buffer overflows and integer overflows are rooted in improper handling of memory or data size limitations. The wolf relies on careless assumptions about input size, but we do not make careless assumptions in Professor Piggy's classroom. Beyond memory issues, we must also understand other injection attacks that target server applications. Injection attacks occur when untrusted input is interpreted as code or commands by the application. These include dynamic link library injection, lightweight directory access protocol injection, and extensible markup language injection. Each of these exploits insufficient input validation and improper handling of user-supplied data. Dynamic link library injection involves inserting a malicious DLL into the memory space of a running process. A dynamic link library is a compiled collection of functions that applications can call to perform specific tasks without rewriting code. In a DLL injection attack, the attacker forces a process to load a malicious DLL, which then executes attacker-controlled functions within the context of that process. This can allow privilege escalation, data exfiltration, or persistent compromise. Lightweight directory access protocol injection targets applications that use LDAP to query directory services such as Microsoft Active Directory. LDAP defines the format and method for querying objects like users and computers in a directory database. If an application constructs LDAP queries directly from user input without proper validation, an attacker may manipulate the query to retrieve unauthorized information. Input validation and parameterized queries are essential defenses against LDAP injection. Extensible markup language injection exploits applications that process XML data without validating its structure or content. XML is a markup language used to store and transport structured data using custom tags. If an attacker injects additional XML elements into user-supplied input, the receiving application may process unintended data, potentially creating unauthorized accounts or altering records. Strong input validation and proper parsing techniques are required to prevent XML injection vulnerabilities. Directory traversal is another injection-style attack that attempts to access files outside the intended directory. Attackers use directory navigation sequences, such as .. to move up the directory structure and access sensitive files. If a web server fails to sanitize input and restrict file system access, an attacker may retrieve critical files such as password databases. Proper file permissions, secure configuration, and validation of file path input help prevent directory traversal attacks. Finally, we arrive at cross-site scripting, commonly abbreviated as XSS. Cross-site scripting is a web application vulnerability that allows attackers to inject client-side scripts into web pages viewed by other users. In reflected XSS, the malicious script is included in a request and reflected back in the server's response. In stored XSS, the malicious script is saved in a database or trusted location and later served to users who access the affected page. The primary defense against XSS is robust input validation and output encoding within the web application. Developers should ensure that untrusted data is never executed as code in the user's browser. Security frameworks and encoding libraries can sanitize HTML and script content before it is rendered. The wolf may try to hide his script inside a harmless-looking comment field, but with proper validation and encoding, his tricks are reduced to harmless squeaks in the mud. OWASP includes more than 10 rules that developers can follow to prevent XSS attacks. As future security professionals preparing for CompTIA exams, you must recognize that most of these attacks exploit improper handling of input and memory. The core defensive principles are secure coding practices, input validation, least privilege, proper error handling, and timely patch management. When you understand how these vulnerabilities function at a technical level, you are far less likely to be fooled by the wolf's cunning attempts. Like and subscribe for more cybersecurity wisdom from your favorite professor, and until next time, stay secure and keep those systems patched. Oink.